This set of videos covers the modeling of composite parts whose manufacturing requires complex tooling geometry. Specifically, what I mean by that is parts which are manufactured using multiple tools, where these tools are ultimately brought together either for a co-cure of the part or post-bonding of the separate laminates into a single part. Some new terminology on how this is represented in HyperMesh. Each of these separate laminates is defined using what's called a sublaminate. And in the case of something like an I-beam, this could be 4 separate tools or sublaminates, a top and bottom plate, and then a left and right web. And ultimately, these tools and sublaminates are brought together into a final part, and how the sublaminates connect is defined by what we call an interface laminate in HyperMesh. In general, it's suggested that sublaminates and interface laminates are only used for the purposes of modeling these complex geometry use cases, and it is not suggested that they're used for simply organizational purposes. For this tutorial, we're going to be using a simple I-beam model. We have a couple T-junction edges, and interface laminates basically are going to be used anytime you do have a T-junction in a composite part. And like I mentioned previously, we'll be defining these 4 sublaminates, top and bottom cap, left and right web, and joining them together into an interface laminate. And finally, unit system for this model is IPS. Modeling process for these complex tooling geometries is very similar to what we covered in the introductory set of tutorials. We'll start with defining template properties. In this scenario, we'll actually need 2 because we have 2 different offsets. We'll review our orientations, specifically our stacking direction and our material reference orientation. We'll get into creating ply shapes and plies. In this case, we'll need to define multiple laminates instead of just the one. And then we'll finish with the steps unique to this complex tooling geometry modeling process, specifically how we define interfaces, or how the sublaminates come together and join ultimately. And we'll do some manipulation of what we call Plies Normals to achieve consistent orientations where the stacking direction on a given tool is not consistent. When everything's fully defined, we'll finish with visualization to verify that all the new input we've provided is correct. We'll begin by opening our tooling geometry file and defining template properties. So I'll go File, Open, Model, and we can navigate to this I-beam Start HM. At this point, this is just a meshed geometry. There is already a material and a local system, which we'll ultimately use for a reference orientation. Other than that, we're building everything from scratch. With the Composite browser open, I will create 2 template properties. I'll give them names. And the reason I need to create 2 is based on where my mesh is located. For the purposes of this example, and typically a convenient way to define these T-junctions, is to have the elements located such that the web elements are at the midplane of the laminate and the caps are at the tooling geometry. At the midplane, it's essentially arbitrary which way they stack, as long as we take care of our bookkeeping, which we'll do at a later point. And for the caps, typically we're simply stacking away from our tooling geometry, up and down on the screen. So to achieve that, for my caps, I'll enter a Z0 of 0. such that the mesh represents the tooling geometry. And for my web property, I'll leave Z0 blank, which by default in OptiStruct is the midplane. We'll go ahead and assign these with a right-click Assign. Holding Alt right now is a convenient selection method. And same thing for the web. And that completes the creation of the template property. In this video, I'll review the stacking directions and the material reference orientation in the X direction. Starting with the stacking direction, I'll do a right-click Orient. We'll go to Element Normals and select all elements. Based on the previous discussion, typically the way I want to model these T-junctions is to have the caps normal direction stacking away from the web at both ends. It looks like that's already correct. And then just to ensure that the web stacking direction or normal is consistent, which it is. The specific direction it points for our purposes at this point is arbitrary. But because of some bookkeeping we'll be doing later, just verify that with the front view shown, your web element normals are going from right to left on the screen. For the material reference orientation, no changes from the introductory tutorial. We'll come over to the reference orientation tab, select all my elements, and I'll use a system method with the predefined local system. Go ahead and assign, and that completes my stacking direction and material reference orientation assignment. This video covers creation of the ply shapes we're going to be using. The 5 are going to be a full top cap, like shown in plies 1, 2, and 3, a left full web, as shown in 4, 5, and 6, a right web only, and you'll note this is just the geometry of the web and not the cap. Additionally, on the right web, we'll have a right full selection, or ply shape, shown by plies 8, 9, and 10 on the screen. And finally, we'll have a full bottom cap shape, shown by plies 11, 12, and 13 here. In HyperMesh, I'll go ahead and begin creating these. I'll just create them first, give them names to keep the bookkeeping easy. And then I'll come in and make my element selections. For this example, it's convenient just to hold Alt for a face selection. Grab my top cap elements, my left full web elements, just verify I got that whole selection. My right web elements, my right full elements. Again, still just holding Alt at each of these selections for the by face option. And finally, my bottom cap elements. This video covers the creation of the plies and laminates which make up this I-beam. I suggest having on a second monitor this slide open, just so you can view all the laminates and plies that we're going to be defining. And I'm actually going to do the same thing here. So to start, I'm going to create my laminates. This isn't mandatory, but I find it's a little bit easier for the purposes of bookkeeping. And I'll begin with the creation of my interface laminate. I'll give it a name, and I don't need to touch anything else here manually if I don't want to. I do have the option of specifying the type explicitly, but when we do this next operation, that will happen automatically. Next, I'll create my 4 sublaminates. Give them each names. And I will finish by shift selecting and dragging these 4 sublaminates into my interface. And after I've done that operation, we can see I get an interface laminate type for my top level laminate. And in my tree structure, if I come to any of these sublaminates, I have the appropriate type for each of them. Now I'll create my plies. I'll go ahead and do a right-click create ply. Again, it isn't mandatory that you do it this way, but I find it's generally convenient. The name, I'll go ahead and just populate the common data, so specifically the thickness, which is a 0.01 or 10 thousandths, or an IPS again. Material, I'll select my material, and I'll leave the rest of the information blank for now. I have 13 total plies, so I'll go ahead and duplicate this by another 12 times. And while I'm thinking about it, I'll just shift select all of these and auto color them. Makes visualization and verification that we set everything up properly later just a little bit easier. Once that is complete, I will begin stacking them and then finish populating the data once they're in the stacks. So I'll select plies 1, 2, and 3. These go in the top sublaminate. 4, 5, and 6 are in the left sublaminate. 7 through 10 are in the right sublaminate. And 11 through 13 are in the bottom sublaminate. At this point, I'll finish by setting my orientations and my shape for all plies in all sublaminates. Note, while it's important to get your sequence correct, the order, whether it's up or down, is at this point arbitrary. This, for example, could ultimately be defined as equivalent to what I'd previously input, and that's all determined when we set our interfaces. And that completes the creation of all the plies and laminates for this model. Note, we're not quite done defining the interface, and we do also have to handle Plies Normals, which we'll talk about in the next video. This video covers the interface definitions of our sublaminates. Sublaminates are ultimately joined together in an interface laminate, and on that interface laminate, we have these interface definitions. Specifically, at each location that a unique pair of sublaminates come together, we need to define an interface. So in this I-beam example, we have 5 unique locations. Interface 1 defines where the left sublaminate comes into contact with the top cap sublaminate. Similarly, interface 2 defines the right sublaminate to our top sublaminate. Interface 3 is from right to left, and 4 from left to bottom, 5 from right to bottom. Interface definitions are always specified using plies, and specifically the ply at either the top or the bottom of each sublaminate. Whether the top or the bottom is chosen determines the ultimate stacking sequence up or down of a sublaminate in the total interface laminate model. Note that the plies we're choosing when we define these interfaces don't necessarily need to share elements themselves, only their sublaminates do. And that's why this ply 7 or web ply is included in the example. The sublaminate in total for the right web wraps all the way around the I-beam geometry, but you'll notice this yellow web ply does not. It only covers the web. However, when we go to define our interface between the right and top sublaminates and the right and bottom sublaminates, because we want this ply 7 on the top of the stack or farthest away from our tool, it's still actually the ply that we'll use to specify those two interfaces from the right sublaminate. Finally, the order that we specify these interfaces in matters, and specifically that order is in the direction of the stacking normal or element normal. So for example, our element normals on the top cap are going up on the screen, and so on the left side I would define my ply 4 in the interface first and my ply 3 second. Similarly, on the right side, I would define my ply 7 first in the stack and 3 second. I'd mentioned previously that the normal on the web elements was essentially arbitrary, and it is, but we do still have to pay attention to which direction it's going when we set these interfaces. Because we chose a normal to the left on my screen, I need to set an interface here of ply 7 from the right sublaminate to ply 4 on the left sublaminate. And when I go to define these in HyperMesh, I find it's easiest to either have a small PowerPoint image like this or to just draw a sketch on a piece of paper and write down what interfaces you're going to ultimately define. Makes it a little bit easier, just bookkeeping, when we go to apply these actual operations. In HyperMesh, and again using that PowerPoint slide as a guide, I can set my interfaces by selecting the interface laminate, right-clicking, and coming to interfaces. This will give us the interfaces dialog, and I'll go ahead and add my 5 unique interfaces here, and then I'm simply going to read off the screen and provide these assignments. So interface 1, ply 4 of the left sublaminate to ply 3 of the top sublaminate. Interface 2 is ply 7 of the right sublaminate to ply 3 of the top sublaminate. Interface 3 defines the web interface, and that's from ply 7 in the direction of the normal to ply 4. Similarly, interfaces 4 and 5 are for the left to bottom interface, so ply 4 to ply 11. And on the right side, we're interfacing from ply 7 to ply 11. Once we've provided those interfaces, that fully defines our interface laminate. The last item we need to manage for a typical interface laminate model build are ply normals. The use case that these solves are situations, again, where you typically run into them on interface laminates, where one or more tools do not have consistent element normals. Specifically in this example, on my right web tool, as I wrap plies from the bottom of the tool around into the web and back to the top cap of the tool, we can see that the element normal is consistent. If I unfolded this ply such that it was flat, all element normals from these different regions would be going in the same direction. Conversely, on the left side of this I-beam in this example, if I wrap a ply from the bottom of this left web tool around into the web, we can see that the element normal or stacking direction flips 180 degrees. It's important to manage this stacking direction on these web sections in this example because of the ply orientations. Specifically, the ply orientations are a rotation about the stacking direction using the right-hand rule. And if my element normal or stacking direction rotates 180 degrees at any location through the ply, I'm going to see the same result in my ply orientations. The solution to fix this problem is I can specify a local ply stacking normal for any individual or selection of plies, ultimately such that the orientations of those plies are consistent as I wrap around my tooling geometry. To do this in HyperMesh, I'm going to focus on the left-hand web because all the other normals I have are consistent. I'll hop back into HyperMesh. And the tool we use to do this is under right-click Orient and Ply Normals. I can view the current normals by clicking Apply and toggling through any plies. We see that 1, 2, 3 are consistent, but when I get to 4, 5, and 6, these normals are inconsistent or flip 180 degrees as we wrap around the tool. Where conversely, for example, ply 8, the normals are consistent all the way around. So to fix this on those 3 plies defined in the left sublaminate, I'll go ahead and select the first one, ply 4. I'll select my elements. I'm holding Alt again for a by face selection. I'll toggle to reverse, and I'll apply. I can verify that I had the correct reverse by flipping back to display and clicking apply again. And now we can see for this ply 4, my element normals as I wrap around my tool are consistent. I'll go ahead and do the same operation for plies 5 and 6 by selecting ply 5, grab my elements, select reverse, and apply. And I'll just verify that change is correct. Same thing on ply 6. Grab my elements, reverse, apply, and back to display. I'll go ahead and just toggle through the rest of my plies here to verify that all the local ply normals are consistent, which they are. This video covers visualization for interface laminates. In particular, to verify that my bookkeeping is correct and I input all the specifically interfaces and ply normals correctly, I like to use 2 visualizations. The first is a detailed thickness view with ply layers turned on. And I'll go ahead and just scale artificially the thickness a little bit so it's easier to see. And specifically what I'm looking for here is consistent ply shapes, in particular as I wrap around this complex T-junction geometry. So for example, I can come to my top, or we'll go bottom cap, and see that I have those 3 full bottom cap plies. And then on my right side, I have my 3 full web plies. I have the center web ply, which was added on our right sublaminate. And then same thing on the left side here. I have those 3 full left sublaminate plies. If the interfaces were defined incorrectly, for example, if I come to my interfaces, and we'll go ahead and redefine interface 4. And let's say I got it backwards. I had ply 11 first and ply 4 second. Typically, I'm going to see something like this on the screen that makes it obvious that I got one or more of my interfaces backwards. And to fix that, I'll just come back to my interfaces here and redefine this interface. And the correct input is ply 4 to ply 11. The other visualization I like is to look at my fiber directions, and in particular to verify on any plies that I assigned ply normals to verify that those fiber orientations are consistent as I wrap around geometry. So I'll turn that on with a right-click, Review Orientations, and Ply One Direction. Things are as expected on the top sublaminate. Then if I come to the left sublaminate, no changes from the 0 degree ply. If I go to ply 5, for example, I can see that my fibers wrap along the top cap and consistently onto the web and bottom cap. Usually what you'll see if you've not defined a ply normal on the correct ply is, I'll go ahead and clear the table that data is assigned on. If I come back to my ply 5 now, you'll see at one or more locations along the T-junction edge usually, the fiber direction essentially rotates 90 degrees. And that's because I have my ply normal incorrectly defined. I'll go ahead and grab my table again for ply 5. And if I refresh the orientations, we can see that that is consistent. And with that, that concludes the model build on an interface laminate to cover the complex geometry use case.